All right. So today we are dealing with class 9. So the daily quiz for today that is going to count as your attendance is daily quiz number 9. Please go on Gradescope and answer that. There is also a fake exam I have posted on Gradescope. Of course, it is optional, but it will allow you to practice uploading documents to Gradescope if you need to practice that. Let's see, today is Feb 23rd. Our exam is coming up on Friday of this week. What is due in terms of homework? Homework 4 is due tonight. So make sure you submit that on Gradescope before 11:59 p.m. Eastern time. And I've also posted homework 5, which goes over K-map problems. I would encourage you guys to attempt these problems before the exam. They are not due until after the exam. So they're due March 2nd of that. So that's Tuesday of next week. In terms of Studio 2 is due tomorrow. So make sure that you get a checkoff from the TAs and undergraduate student assistants, and also submit a report, a group submission. You guys are working in as a team of 2 on Gradescope. So both things are required. In terms of next Studio 3 resources and a video link, all of that has been posted on Piazza under Studio resources. So take a look at that. Now let's come to the main topic for today, which is going to be not today, but I'm sure you want to know more about this. Exam 1 is Friday, Feb 26th, and I have posted several documents on Piazza indicating what are the topics, what are the logistics, and I have provided hints about, okay, can you reduce your scanning and uploading time. So please make sure that you read in detail about the logistics that are involved with exam 1. When is it going to be available? By what time do you need to start to get the full 2 hours, 30 minutes? So read through that document pretty carefully. There's a question online. I may have missed this, but is there a class meeting on Friday or only the exam? Just the exam, Peter. No class meeting. Can we use an iPad to fill out the written part? That is kind of, questionable because not everybody has an iPad. But, for those of you who have it, go ahead. You can use iPad. Yeah, that's okay. As long as you are showing all your work, that is what we will be looking at. Okay. Let's see. All right. So we have been talking. The plan for today is I'll try to wrap up our discussion on K-maps, and then I will circle back to exam 1, and I'll take your questions, and we can talk about logistics if we need to. That discussion will also be recorded. But today, we'll start off with our continued discussion on K-maps. We stopped over here. We were looking at why Boolean algebra is not a very good way of logic simplification, and what K-map allows us to do, right? Like a very systematic approach to logic minimization. And if you follow all the rules, it guarantees you with the simplest SOP, or simplest product of sum expression. And this is the example that we did last for a 3-variable K-map. You have 3 inputs A, B, C, and you have 1 output F. We tried to indicate each cell in the 8 cell K-map with a number which corresponds to a row number in this particular truth table. So we have 0 through 7 as our row numbers that correspond to cells 0, 1, 2, 3, and then 4, 5, 6, and 7. And that switch is because of the requirement that only one variable can change to establish adjacency. So that's why we kind of swapped these 2 columns in order to maintain that. And our goal while we did all of this was to create as large of a group as possible. And in this case, if we are going for a sum of product, we are going to make a bigger group of ones as opposed to a smaller group of ones. We are going to try to make as big as possible and as few as possible. So we started asking questions such as, in the 3-variable case, can I make a group of 8 ones? Clearly, there are a couple of zeros, 3 zeros in fact. So we said, no, that cannot happen in this case. Then we asked another question, can I make a group of 4 ones? That was also not possible. And then we asked a question where, can I make a group of 2 ones? And as you can see, it only has a powers of 2. Whenever you are grouping ones or zeros, those groups should include ones or zeros, but the number of ones and zeros should be a power of 2. And then we had, I think, 3 groups of 2 ones. We indicated that with a green box, a purple box, and a blue box, and we got those product terms listed. And then there was also a singleton here, which we also listed at the very front. Can you switch the rows? Sure. So if you switch the rows over here, you have to make the adjustment in your K-map as well. So like I said, some people choose to have the K-map this way. Some people may choose to have the K-map. Let me draw it over here. Sure. So some people may choose to have the K-map laid out vertically. Right? That's totally fine. That works as well. In fact, you can have ABC or you can have BCA. You can have any. So all those things are possible. The things that change is the numbering scheme over here, right? So the row numbers or the cell numbers need to correspond to each of these entries when A0, B0, C0, and so on. So as long as you're maintaining consistency, it doesn't matter whether you have ABC listed or BCA listed, whether your K-map is laid down horizontally or like this vertically. It doesn't matter. I mean, on the K-map for C, can you do 1, 0? So if you do 1, 0, sure, yeah, you can do that. Absolutely, that works. So, the only difference is the expression that comes out of it is also going to be different, right? So if this was 1 and this was 0, then that particular group would not have C complement and B, that probably will have C and B, right? So you have to adjust the corresponding product term as well. All right, so let's see. We talked about that. Let's start with an example. Here we have another 3 variable K-map. We still have ABC as our input variables. And this is related to some logic output F. And I've already placed in the ones over here. And I've left 2 empty spots over here and over here to simply indicate that when you see blank spots, that mean a 0. So this is something, it's the same thing as saying there are zeros over here. So sometimes you may see them as blank. That simply means that there are zeros over there. But if a truth table has ones and a zeros and don't cares, then those don't care situations absolutely need to be explicitly drawn and listed in the K-map. In this case, we are just dealing with ones and zeros. So if I leave it blank, that essentially means that those are zeros. All right, so let's start with the question. Can I make a group of 8 ones? I really don't know the follow-up to that. All right, so no, right? Like the WebEx chat box explodes with no. All right, so I can't make a group of 8 ones. So next question, can I make a group of 4 ones? I know what Andrew's answer is going to be. All right, yes, all right. So let's try to see what those groups are. So a couple of things to note here. Edges wrap around, right? So if edges wrap around, I will be able to group these 2 guys with those 2 guys. So I've got a group of 4 ones over there. And then let's see if we can make another group. Another group of 4 ones. Can I do that? I thought if 0, 0, 1 and 0, 1, 1 were don't cares, you can make them a 1 in this case to simplify it. Yeah. Absolutely. But I'm saying that these are not don't cares, these are zeros. So blank spots are zeros. If you had don't cares, then you would need to explicitly place them in the K-map. You cannot just, have an empty cell. So this was under the assumption that those are zeros. Let's see. Now, can I make so let's see, bottom row. Yes, absolutely. I've got another group of 4 ones here in my bottom row of 4 ones. And as soon as I finish this, I have covered all the ones and I'm done. That's it. I don't need to make any more groups, right? So I've completed my objective. I've made the biggest group as possible and as few of those groups as possible. I've covered all the ones and that completes the grouping. Next, I just need to write the corresponding product terms. So what about the red wraparound group of 4 ones? What is going to be the product term for that? Let's see. A is 0. A is changing. B is 0. Right? So if B is 0, that would be B complement. And it looks like C is changing as well. So that's it. I only have B complement, nothing else. And for the other group of 4 ones, A is changing, B is changing. The only thing that is remaining the same is C, and in this case, C is 1. So that would give me C. So my function is B complement or C. Naif says he cannot wait for a 5 variable K-map. All right, we'll get there as soon as we finish 4 variable K-map. So that's it. That's all I have. That's my simplest SOP, right? My simplest SOP, because I was looking at combining the ones. And it just so happens that this is also the simplest POS. More about that later. How do you deal with the POS? Because then you will be starting to look at combining the zeros. We'll do some more examples about that later. Okay, so now let me try to discuss a very important connection between Boolean algebra and K-map. This is sort of your backup wherever you get into trouble with Boolean algebra, right? Sometimes you might get into a situation where you're not seeing the next step in Boolean algebra. So what you can do is you can leverage your understanding of K-maps in order to guide your Boolean algebra simplification. You would not switch over the simplification to K-map. You would just be using the K-map in order to guide you in terms of next steps for as far as Boolean algebra is concerned. So I find this very helpful. So let's take a look at what it looks like. We are starting off with an example here where f is a SOP expression. I don't know if it's the simplest or not, but I'm just assuming that this is a SOP expression with 2 variables x and y, and that's how they are related to f. So in order to show you that connection, the first thing that I'm going to do is enter the corresponding ones in the K-map. So the first term over here, let me highlight that in green, for example. X and y complement, that essentially means that there is a 1 in the cell where x is 1 and y is 0. So where would that be? X is 1 and y is 0 would be right here. So that goes to a 1 because of that particular product term. Again, our answer is in a SOP form, so that's the reason why we are entering 1s and not 0s in the K-map. Now, next, let's see. Where would x and y go? Well, x should be 1, y should be 1. So that would be right here. And that should also be 1 over there. And then the last term here is what? Let's say pink. X complement and y. X should be a 0 and y should be a 1. So that should be right here. and there would be a 1 over here as well, right? So now the question is, okay, in order for me to continue with my Boolean algebra simplification, I would probably need to duplicate some product terms in order to combine more, right? You have heard me say that. Duplicate terms to combine more. Now the question is, which term should I duplicate? I have three options. Now, in order to understand which term to duplicate, let us leverage our K-maps. So when you make over here, when you are trying to combine the ones, what are you trying to do? Clearly, you have a vertical group and a horizontal group. You guys agree with that? So there is a vertical group here of 2 ones, and there is a horizontal group here of 2 more ones. And if you observe here, this cell right here is being reused twice, right? So it's being reused in one group as well as in the other group. So that tells me that that is the particular product term that is being used. So I should duplicate that one. One of them will get combined with that, the other will get combined with that. So you see how you can use your K-maps to help you find that term to duplicate. So what is that term? That's the blue term, right? So that's right there, right there. So let's say I'm going to say duplicate. And then I've got the next step, which is x and y complement, or x and y, or x and y. Clearly, I've duplicated them just 2 times. The reason being it was used twice. It was not used 3 times. If it was, then I would duplicate it 3 times and combine it 3 of those terms with 3 other things. Let's see, what else do I have here? The last term, x complement and y, right? So I've simply duplicated this twice, and the other terms are as is. Now we can see that this guy is going to combine and this guy is going to combine. You can pull out a x from the first 2 terms, and when you do that, you are going to get y or y complement, which is simply x. These are color coded, by the way, with the red box. And then from the second 2 term, you have y pulled out, and then you've got x or x complement, which is simply y. And that is exactly what we have in the K-map. This is y and this is x. And this kind of helps you see that connection between Boolean algebra and K-map. So if you get into like a very tough spot and you're not able to see which term do I duplicate, which term will be able to combine more, then you can use a K-map by the side to guide that manipulation. Just a word of caution here, you are not transitioning from Boolean algebra to K-map. You are simply using the K-map to guide your Boolean algebraic simplification. Questions about this this concept? All right, so it looks like you guys have it. Let us now try to increase the size of our K-map. Now we go to a 4 variable K-map. Over here we need 4 input variables. In this case we are using A, B, C, and D, and some arbitrary output F. So I've listed simply all the possibilities of A, B, C, and D. They would range from all the 4 zeros all the way down to all 4 ones. And if I were to write the row numbers for F, I would start with 0, 1, 2, and so on up to 15. And at each of these locations, I may have a 0, I may have a 1, or I may have a don't care. And then, so just because I'm doing this as an example, I've already entered the ones in the K-map. So there were some zeros and ones in my output column, and I've already placed them, I've already entered them in their corresponding cells for the 4 variable K-map so that we save time. But I want to show you how I've chosen, right, this pattern of distributing which input variable on which row and which column. I stay consistent with that. So I stay consistent in terms of this. If you look at the order, I've got A, B, C, and D. So A is behaving as my most significant input, and D is behaving as my least significant input. So in order for me to kind of do this very quickly, I choose one pattern and I stick to it. What I mean by that is I always choose A, B, then C, and D in that same order. I can still change that. I can have A, B over here and C, D over here, but all my numbering scheme will have to change based on that. So just so that I gain some speed and save some time here, how do you find don't cares? Right now there are no don't cares. I have to be given them in the truth table. We are still dealing with only zeros and ones. So my numbering scheme is going to be, if I choose A, B, C, and D that way, I have A, B for the 4 columns and C, D distributed on the 4 rows. And if you observe, we still have that same adjacency criteria for both the rows and the columns, right? 0, 0 to 0, 1, only one variable changed. 0, 1 to 1, 1, only one variable changed. And the last one, only one variable changed. And the same now applies even for the rows. In the 3 variable K-map, we didn't have to worry about that because it was just one variable there and one entry was 0, the other entry was 1. So how is my pattern looking like? Because I have chosen A and B first, and that is 0, 0, I'm going to start the numbering like this: 0, 1, 2, 3, 4, 5, 6, 7, switch 8, 9, 10, 11, 12, 13, 14, 15. So if you follow a particular pattern, and you can have your own, whatever you feel comfortable with, you can choose that. But that's the one that I use, and I always try to use that so that I don't get lost with the numbering. So for example, I could have done 0, 1, 2, 3, but I'm not doing that because that's the way I chose to distribute my input variable. Now, I've put in some arbitrary ones in there. All my empty cells are zeros. Question 1, can I make a group of 16 ones, right? That's the first question you will ask. 16 question mark. We are still doing SOP. And the answer here is no, because you see some empty slots, empty cells in which there are zeros. All right, so next question, 8. Do you guys see any 8? All right, still no. How about 4? I think there are going to be a few 4, a few of them, right? So let's see. In using the cell numbers, can you guys talk about which cells would you combine with which ones? Edges, wrap around. So Andrew says 0, 2, 8, and 9. 0, 1, 8, and 9. Okay, so let's see. 0, 1, 8, and 9. All right, so that's a wrap around horizontally, right? So that's going to look like this. Let's use blue for that. All right, so that's good. And then let's see, 0, 2, 8, and 10. So 0, 2, 8, and 10. All right, 4 corners, beautiful. So that works as well. So yes, let's use pink for that. Sure, let's that, and that. All right, so I've got the 4 corners also can combine. So that's good. What next? I think 14, 10, 12, and 8. 14, 10, 8, and 12. Again, edges wrap around, and in this case, it is the vertical edge. So that is also going to be a good one. Let's see. Let's use green for that. as big as possible and as few as possible. Okay, what else is left? So it looks like I have two more ones that are kind of without a friend right now. Yeah, that's all for fours. Yeah, you are right. So we have got three groups of 4 ones. 1, 5 and 15, 14. Right, 15, 14 is the only option. 1 and 5 are the only option. That's it. So we have a, in this case, our simplest solution is kind of a unique solution for this particular example. Not going to be the case in general, but in this case it does. Let me use purple for that. All right, so I've got one group there and the other group there. Wonderful. So I've got those two as well. Right, so let's see. And then I have 2 question mark and then we listed 2 of them. So now we can talk about the product terms that correspond to each of those groups. So let's start with, let's try to stay consistent with the order. So I think the first thing that we did was blue, right? So for the blue guy, let me use there. What is that going to be? Let's see. B is 0 and C is 0. Right, so that would be B complement and C complement. Others are changing, so we don't need to worry about that. Next, pink one. 4 corners. B is 0 and D is 0. So we have got B complement and D complement in that case. I hear you, Matthew. They are so much fun for me too. Let's see. Let's go to the green one now. So for the green one, what do we have? A is a 1 and C is a 1. So that's A and C. Did I do that right? A and, oh no, not C. D complement. Right? D is 0 here, D is also 0 there. D complement, yes. Let's see, what else? We got the 4s. Now let's go to the 2s in purple. What about this guy? 14 and 15. A is a 1, B is a 1, C is a 1. All right, so that's good. A, B, and C. And right away you see that the moment we went from a group of 4 to a group of 2, our product term has one more literal, right? So it's become more costly. That's why we prefer a large group in order for the number of inputs to that AND gate to be as small as possible. All right, we have one more thing left in terms of 1 and 5. So let's also try to list that right here. Looks like A is a 0, C is a 0, D is a 1. Yes, A complement and C complement and D. I think that's it. And then everything together is going to be your F. So F equals, it doesn't really matter which one. C is changing from the green term we just did. Why don't we include C? So green term. So for green term, this and this, right? A is a 1, B is changing, so that gets eliminated. And if you observe, 0, 0, 1, 0. C is changing, gets eliminated. D is a 0, that stays as D complement. All right, so let me go back to F. It doesn't really matter in which order I express them. A, B, C, A complement and C complement and D, and A and D complement, B complement and D complement, B complement and C complement. Now, if you were given this expression and asked to simplify, you would probably not have a very good way of claiming that this is in its simplest form already or not, right? So that's the advantage here. If you follow the rules, you are guaranteed that this is going to be the simplest SOP. We don't even need to, worry about whether it is or not. Right? For an expression like this, it might not be obvious whether it is simplest or not. All right, questions about 4-variable K-maps. It looks simplest. How does it look simplest? Okay, for me it doesn't. All right, so for me it doesn't because there is a there, a there. You know, it's not very obvious to me. I would spend some time trying to look at whether I can combine things with others. If I was not using a K-map to guide this, then it would take me some time. Eventually, I would understand that, yeah, this is the simplest, but it would not be very, very obvious. Let's see, are K-maps only used to generate SOP or can we use it to POS as well? It is used for SOP, POS, both. Are we given the truth table and then we solve the K-map? If you are given the truth table, you can go to a K-map, or if you are given to a K-map, you can go to a truth table and also simplify it. But you're right. You would need to have some logic representation so that you can make a K-map out of that. Right now, I have put some arbitrary ones and zeros. So this is an assumed truth table. I could have given you guys a Venn diagram, for example, right? So I could have given you a 3-variable Venn diagram, and depending on where I shade or not shade, you could translate that into a K-map. So, and if you want to be really particular about that, you could go from a Venn diagram to a truth table to a 3-variable K-map. You're right, Andrew. You just group zeros instead of the ones, and you think of the changes between minterms and max terms. Can you turn f into a K-map if they? Can you turn f into a K-map if they're not all minterms? Can you turn f into a K-map if they're not all minterms? I'm not sure what you mean by that. So, for example, if say I had the expression, right? So suppose I had this expression. These terms are clearly not minterms. Of course, none of them are, because I would need all 4 variables. But if we try to take this particular term, for example, a and d complement, that simply means that a is a 1, d is a 0, and you have all the 4 possibilities between b and c, right? 0, 0, 0, 1, 1, 0, 1, 1. That's where you would enter the 4 ones. So you would get 4 minterms for that particular term. All right, other questions, you guys? Okay. Now let's talk about don't care situations. Now the goal gets adjusted a little bit when you start putting in don't cares into a K-map. Where are these don't cares coming from? Well, you fill out a truth table for a logic representation, and in your truth table, especially the output column, you will have a few zeros, you will have a few ones, and for some input conditions you don't care, then that's where you will have an X. But if you take that, in this case it's a 4-variable K-map, it's a 4-variable truth table, so there are 16 rows, and you translate that into a 4-variable K-map and enter the zeros and the ones and the X at appropriate locations, how do you deal with simplification? Well, the goal gets adjusted a little bit. The goal is still to cover all the ones, but the goal is not to cover all the don't cares. You would simply combine the don't cares only if it helps you make a bigger group. Let me write that down over here. Include don't cares only if it helps to make bigger groups. But your goal is not to cover all the don't cares. Your goal is still only to cover all the ones, and that's for the SOP case. So let's start with the question. Can I make a group of 16 ones? 16 question mark. No, there are a bunch of zeros there. So the answer is no. How about 8? You guys are wishing, you guys are, looking at this, aren't you? If that was a 1, you could have made it into a group of 8. Or that. All right, so no, right. You're right. So no. You can make a group of 8. I think we can do a bunch of 4s. So let's see. How many 4s? So the answer is yes, right? Like, can you make a group of 4 ones? Sure, the answer should be yes. Let's try to see how many we can make. And again, can you guys, I'll try to, go through this process. At any stage you guys have a concern about the group, let me know. So the first thing that I would notice is the horizontal edge. So right here, I've got these 2 guys and those 2 guys. That's going to be my first group. And then I'm going to look at this particular one. And I'm going to try to make a big group of this, as big as possible. So it looks like I can do all of those. So that's going to be my second group. Andrew says 3 of them. Let's try to see. So I've got that. I still have a few ones left out. How about this? This particular one, I have a 0 there. So the only big group that I can make here is that. I'm going to put that in a box as well. I still have 2 more ones left. Now, if I look at this particular one, what can I combine it with? Well, it looks like I can only combine it with this guy. That's it. That's the only way. What about this guy? This guy, I think this is it. Right. So Andrew is right. We were able to make 3 groups of 4 ones. And then we made 2 groups of 2 ones. So now let us try to, and you can obviously write in the product terms for each of those groups, and we'll do that as well. But before I do that, I want to talk about what is the difference between that particular don't care and this particular don't care. Let me highlight them, one in blue and one in yellow. What is the difference between this guy and this guy? Well, when you make it part of the group, the top one is used to simplify, yes. So you're treating that don't care as a 1, right? So you're treating that as a 1 here, and you're treating this guy as a 0 here, right? So when you actually make this into a circuit, you implement this particular simplified SOP for the case when A is a 1, B is a 1, C is a 1, D is a 1, the light would be on, the function would be true. If you choose to implement it using the simplest SOP, which is the result of this particular K-map. However, for this don't care, because we left it out of the group, it's being treated as if it was a 0. Which in other words means if A is a 1, B is a 1, C is a 1, D is a 0, then the light would be off. The function would be false. You guys see that? So don't cares and not don't cares, once you fix the expression that you go on to implement, then they are no longer actually don't cares. You have assigned them a particular value, 1 or a 0. And because you don't care, you don't really care whether light turns on or off in that situation. All right, so let's try to finish up this example with the terms. For this guy, what do I have? I have Let's see, D is a 1 and B is a 0. Please, you guys should be checking my work. For this guy, this is simple, C and D, because C is a 1, D is a 1. Let's see, for this guy, I have A is a 1 and C is a 0. Let's go on to the next two terms. For this guy, I'm going to get, let's see, B is a 1, C is a 0, D is a 0. And then I think we are left with only one, right? So this guy is what? This is A is a 0, B is a 0, and C is a 1. Let's see, can we, the question in the chat box, can we use the remaining zeros to confirm that we got everything? If we have 5 groups of 1. So the remaining zeros, because they are don't care situations in this, if you start looking at the zeros, then you're essentially going for either the SOP form of F complement or the POS form of F, right? So there are two things when you start focusing on the zeros. But the logic functions will be related. They might be related directly or they might be related in a complemented fashion. So we'll do an example later on when we'll try all of these concepts together using De Morgan's law. That's essentially De Morgan's law. If you have 5 groups of 1s, then we should have 5 groups of... Oh, not necessary. I don't think that that's any necessary there. Like, it depends on the locations of all those 1s. All right, so that's it. That's your simplest SOP for this guy. So F is A complement and B complement and C, or B and C complement and D complement, or A and C complement, or C and D, or D and B complement. All right, questions about this example, you guys? How we are dealing with don't cares? The goal has adjusted. We have left some don't cares out. Well, we just left one don't care out, but we left a don't care out. So the goal is to cover all the ones. The goal is not to cover all the don't cares. Okay, let's move on to a 5 variable K-map, the thing that we have been waiting for quite a bit. So let us try to look at a good practice and a bad practice when it comes to a 5 variable K-map. So I'll explain that with a slide here. So when you have a 5 variable K-map, let us suppose that you have 5 variables A, B, C, D, and E, right? And then you have, say, an output F. Because you have 5 variables, you are going to have 32 rows in this particular truth table, which in other words means that your row numbers will be from 0 to 31. And now if we start observing how the inputs are going to be laid out, you will see that E will go 0, 1, 0, 1, alternates. E will go 2 zeros, 2 ones, and keeps going. Then this will be 4 zeros, 4 ones, and it keeps going. This will be 8 zeros, 8 ones, and it'll keep going. But over here, for the most significant bit, you will have 16 zeros and 16 ones, right? Let me highlight that. So I really hope this isn't on the test. It is very easy once you get it. And my hope is once you understand this, you actually prefer this compared to this. No. So the beauty about 5 variable K-map is that you can make bigger groups. So, you know, test covers everything, including this, right? Yes, it does. How is this? Why is this becoming so intimidating for you guys? All right, so let's try to. There's just 2 4 variable K maps right next to each other. That's it. One K map when A is 0, and the other K map when A is 1. But they are just two 4 variable k-maps. It's just annoying. If you understand this in the next 2 days. All right, so here, let me try my best to break this 5 variable k-map down for you guys. And let's try to do justice to this. So bottom line is, I can have A as the variable that distinguishes between which 4 variable k-map separates the two. Or I can use E as that variable. But if I use E, you know what is going to happen. Because the 0 and the 1 is going to alternate, you are going to have to jump 1 here, 2, 0, there, there. You are going to have to keep switching back and forth in terms of entry, the way you enter things into the k-map. Which also means that that numbering scheme is not going to be first 16 over here, the last 16 over there. It's not going to be the case. That is why what I recommend, and this will save you a lot of time and headache, is when you look at your truth table and you have your most significant input variable, in this case it is A, choose that as the variable that distinguishes between the left 4 variable k-map and the right 4 variable k-map. After you do that, you can have B, C, D, E over here and then B, C, D, E over here. In other words, when A is 0, you will have 16 combinations between B, C, D, and E that go in the left 4 variable k-map. And when A is 1, the last 16 entries in your truth table, you will still have the 16 combinations between B, C, D, and E that go in the right k-map. So how does the numbering scheme work? Well, it's going to be exactly the same, in fact, for the 4 variable, the first, the left k-map, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Exactly the same as before. And now we are simply going to add 16 to that number and get over here. 16, 17, 18, 19, 20, 20, 21, 22, 23, and so on, all the way up to 31. So we have essentially added 16 to the cell numbers on the left to get everything on the right. And they are exact copies of each other, right? B, C, D, and E, B, C, D, and E, because A is 0, you get 16 combinations of B, C, D, and E. A is a 1, you get 16 combinations of B, C, D, and E. So I'll take a moment here to see if you guys have any concerns about translating a truth table into a 5 variable k-map. All right, so yeah, it's going to be annoying. It is going to probably take a little bit of time, but in terms of the concept behind it and that choice, right? Why did I choose A as that variable? It's not 7, yes. So, if you think about it, if you chose A, B, C, and D over here and chose E as 0 there and E as 1 there, what would you have to do? You would have to go cell 0, cell 1, cell 2, cell 3, cell 4, cell 5, cell 6, cell 7. And it would be a bigger headache than this, right? So that's the reason why I'm saying choose A over here. Choose A as the variable that distinguishes between left 4 variable k-map versus right 4 variable k-map. Okay. 4 dimension k-map. No. We are not going to do more dimensions than this. This is essentially our limit. Like 6 variable k-map is our limit. And even the 6 variable k-map is kind of like for homework purposes, is not for exam purposes. But 5 variable k-map is kind of where we are going to draw the line. And 6 variable k-map is nothing nothing but four variable K-maps. So it would look something like this. So if you have A, B, C, and D, you would have AB is 0, 0, go in the first four variable K-map. AB is 0, 1, go here. AB is 1, 0, go here. AB is 1, 1, go here. So that would be like a 6 variable K-map, but we are not going to do that. We are going to stick with this. All right, Naif has jumped the gun. And whenever he jumps the gun, we usually have fun. So let's see. The first question. Wait, so this K-map would be given on the K-map and we would simplify. No. So I would not give you a K-map. You would need to draw it. So I would probably give you a logic function which I can represent using a truth table, a Venn diagram, a logic diagram, using transistors. We have seen many different ways to express a logic function. From one of those representation forms, you can get the logic function, and now if you have to simplify, you could use a K-map to do that. Go all the way to... No, Matthew, I think I'm going to stop with the 5 variable K-map case. So this is kind of where after this it is just what would worst case scenario look like? A checkerboard. Yeah, that's right. That's exactly right. That would be the worst case scenario, because I would not be able to combine anything with anything. Well, I probably will be able to combine corners, but nothing beyond that. Right? Yeah, the sides maybe, but like if you have one checkered and the other is complemented checkered, then that probably will be the worst case scenario. All right, so let's try to do this example here. The first question should be what? The first question should be what? 32, right? So can I make a group of 32 ones? Please say no, because they are a bunch of empty cells with zeros in them, right? So, all right, 32 goes out of the window. Let me write the questions here. 32 goes out of the window. How about 16? Still no. How about 8? Yes. And where is it? And if you look, think of it as one K map, and underneath there is the second K map. So the group would be box and exactly the same location, another box. 4, 5, 4, 5, 12, 13, yes, and then 20, 28, 21, 29. Beautiful. That's exactly right. So that's our group of 8 ones. So let's try to write the term for that. I'm going to say all right, what is the term there? A is changing, gets eliminated. B is a 1, that remains. C is changing, gets eliminated. D is a 0, that stays. E is changing, gets eliminated. So it's geometrically the K-map is stacked on. Yes, exactly right. So it's like they are stacked one on top of each other. Yeah, it's 3-dimension, but it's easier to see it side by side. But you're right, they are stacked on top of each other. That's where you're making those groups. Isn't B changing? Right. Why did I say B? B is 0 to 1. C is C is a 1. C is a 1. D is a 0. E is changing. Yes. C and D complement. Yes. Thank you. So I'm done with a group of 8. Can I make any more group of 8? Physical K-map with switches and LEDs tagged. that would be something. That would be really fun, fun thing to see how we can do something with that. You flip the switches and your two groups of two. Knife is on a train right now. Let's see. So no group of fours is what you're saying. And then there are two groups of two and three groups. All right. So let's try to look at four. All right. Four is not possible. Come on. Four is not possible. So four question mark no. And then two is the next question mark. And I think you will get a bunch of twos. Let me put them in red. So the first one is going to be right here. The second one is going to be very obvious right here. And the third one, 15, 13, 10, 26, 10, 26, right? That's the one. So let me show 10, 26 this way. So I've got 13 and 15. You have got 27 and 26, and then 10 and 26. Perfect. Now we are ready to write their terms. So for this guy, it is going to be A is 0, so A complement. B is a 1, C is a 1. Not a good place to write this. A is 0, B is a 1, C is a 1, D is changing, E is a 1. They look like singles. I would differently. Yeah. All right. So we'll do that. We'll try to color code them. All right. So let's say next group right here. What do we have? A is a 1. B is a 0. Sorry, B is a 1. C is a 0. D is a 1. And E is changing. And the last one is, let's do arrows. And A was changing, gets eliminated. What is B? B is a 1. C is a 0. D is a 1. E is a 0. Done. So that's going to be my F. F is, the simplest F is SOP. Simplest SOP is C and D complement, or A complement and B and C and E, or A, B, C complement D, or B, C complement D, E complement. Done. What about 15, 13, 12, 20? What about 15, 13? Which one? 12? 15, 13, 12, 20? Oh, can't do that. Can't do that. We can't do that. It can't it be? No, it can't be. Because for these guys, first of all, you're looking at a 0 there. So it's like doing like it's diagonal. Yeah. So in order to keep the adjacency, you have to have only one variable change, right? You cannot have both of them change at the same time. All right, you guys, let's you can only go through one dimension at the same time for the cube analogy. Yeah, that's true. That's another way of looking at it. All right, we talked about 6 variable, just an idea here. If you had a 6 variable, then you would require 4 variable K-maps in which you would take the two most significant inputs as AB, and you would have put 16 go there, 16 go there, 16 go there, 16 go there for AB is 0, 0, 0, 1, 1, 0, 1, 1. So that would be for a 6 variable K-map. And if you kind of go on to this theme, it's like you are increasing the size of the K-map, but you're still following Right, that's exactly right. But you're still following sort of the um, same rules, right? Bigger groups, power of two groups, and as small as possible groups. So in terms of the rules, nothing changes, just the size of the K-maps change. All right, now let's try to look at the simplest product of sum expressions. And if you understood simplest SOP, and if you make a slight adjustment in terms of looking at the zeros instead of the ones, combining the zeros instead of the ones, you are in the you are in the simplest POS expressions. You will be able to deal with that. So I have a 4 variable K-map that I've constructed. I have entered arbitrary ones and zeros in the K-map. There are no don't cares over here. Instead of combining the ones, I will be combining the zeros because I'm going for the simplest product of sum expressions. So I would be asking questions, and the first one I will ask is, can I make a group of 16 zeros? What do you guys think? No, because I see a bunch of ones in there. Next, 8 zeros. Yeah, that's also no. I think when you go to 4 zeros, we will have a bunch of them, right? So the first group that I see, which is pretty clear, is right here. Box it up, box it up. This is like 5D chess now. With practice, things become pretty straightforward, Gavin. I just hang with me. All right, so I hope that that group of 4 zeros was pretty straightforward to you guys. The next one, let me use maybe pink for this. I'm going to draw this. Reuse cells in order to make bigger groups. That's what we did there. So now we have 2 groups of 4 zeros. The next one is going to be what? Let's say green. I've got this guy with this guy. Nothing much we can do there. And the last one, maybe in red, sure. Doesn't have any friends right now. Okay, so let's try to write the sum terms. We have a group of 1. Yes, okay, all right. Now, instead of writing the product terms, we are going to be writing sum terms for each of the groups. So, for the blue box, for the blue group of 4 zeros, what would I write? Think about this. A is a 0 and C is a 0. B is changing, gets eliminated. D is changing, gets eliminated. So A is 0, C is 0. So you would say A or C. Oh, right. So when you are looking at, right, so because you are looking at zeros, you would use a OR operation. So A is 0 or C is 0, those will be zeros. Right, so you would say A or C. So those are the little details we need to be careful of. Next, for the pink group, what do we have? A is still 0 and D is 1. A is a 0 or D is a 1, which means D complement is a 0. Right. For the green, What do we have here? Let's see. P is a 1. C is a 1. D is a 1. C complement. C complement. And I think it's B complement or C complement or D complement. All right, so let's try to look at the last one here. Last one is right there. That is going to be A is a 1, B is a 0, C is a 1, D is a 0. That's it. That's my F. Now I need to do a product between all those sum terms that I wrote. So my answer would be A or C and A or D complement and B complement or C complement or D complement and A complement or B or C complement or D. Done. Simplest product of sum. Questions here, you guys? Yes, that is right. Time to not everything. All right, let's try to take let's ask this question now. What about the don't cares conditions in product of sum simplification? The answer is very similar to what you would expect. You would treat a don't care as a 0 only if it helps you make a bigger group of zeros. Otherwise, you would treat it as a 1 and you would leave it out of the group. And the goal while you are dealing with don't cares in K-maps in order to get the simplest product of some expression is going to be to cover all the zeros but don't need to cover all the don't cares. For the sixth term, 1, you can connect any two. Hold up. And I'm not sure how the wrapping would work. For the sixth term, you are talking about the 4 variable K-map? 6 variable K-map? Yeah, so if you have things that are going across these two, right? Then A is a 0, B is changing, so you would keep the A complement, but you would get rid of the B. And then you will have, C, D, E, and F play the role where that group is. But when you're trying to combine across the 4 variable K-maps, then you can do this or this, this or this, this or this, this or this, but you cannot do this because A, B, and both are changing there. So it's like K-maps of K-maps. Do you see that? So the 4 corners would be what? So if you have 4 corners over here and 4 corners over here, then you would get D complement and F complement and A complement. All right, let's see. Welcome to the matrix. Right, we talked about the simplest SOP. We talked about how to deal with don't cares. Now let's talk about the connection between POS and SOP and the De Morgan's law, which plays a crucial role over here. So in order to go through this example, what I'm going to do is 2 things. One, I'm going to try to find the simplest SOP for F complement. And I'm then going to use De Morgan's law while I complement both sides of the equation I get from step 1. Let me talk about what I mean by that. I have a truth table. I have a 3 variable case, A, B, and C. I have arbitrarily chosen an output F, and I have entered bunch of zeros and ones. Arbitrary choice. What would be F complement? Well, that is simply the opposite of F. So that would be 0, 1, 1, 0, 0, 1, 1, 1. And my first step here is to find the simplest SOP for F complement. Wait a second. I was trying to go to the simplest product of some expression. So why am I going for SOP? The reason is I am trying to get SOP, simplest SOP for F complement, not F, in order to go to the second step and eventually get the simplest product of sum for F. That's the example here. So let's see. I have written down the F complement here. I'm simply going to enter F complement into this 3 variable K map and start grouping the ones because I'm after the simplest SOP. De Morgan inverses the output. Yes. So let's see. Where do I have the zeros? It looks like I have 0, 1, 1, 0, 0, 1, 1, 1. I've entered things. Why not just do the product of sum from the start? You could. I'm just trying to show you the connection between the two. So I'm just trying to bridge that using De Morgan's law. So what would SOP in one mean in POS on the other? That's why. So if you start with this, right? This is the simplest SOP for F complement. So I've taken F complement, all of these guys, and I've entered them into the 3 variable K map. Now what do I want to do? I want to group all the ones, right? Because I'm after the simplest SOP. So can I make a group of 8 ones? No. Can I make a group of 4 ones? Nope. Can I make a group of 2 ones? And I think you guys will say that, yeah, you can make 4 of them. Would you need 4 of them? 3 of them. All right. So let's see. You have got these 2 guys. Then you have got those 2 guys. And then you have got a choice. A choice. You see, you remember I said simplest SOP is not unique. So some person might say I will do this, some other person might say I will do this, and they both would be correct. And they would both have the same cost. But only one is necessary. The other one would be redundant. So I need to only pick one. You technically said how many could you make? All right. All right. So if I really wanted to ask you guys how many could you make, I would ask you to answer this question. Think about a 4 variable K map and answer how many different ways you can have a group of 4 ones. So that would be the question. Okay, so let's come back to this. Yeah, you're right. I said how many? You can make 4 of them, but you would only choose to make 3 of them. Because if you pick the green, then the pink is redundant. You don't need that. And if you pick the pink, then you don't need the green one. So one or the other. Bottom line, simplest SOP is not unique. So Naive says we don't accept circles. All right, so let's just do this then. All right, fine, that works. One or the other would work. Let's see. I have The blue groups would give me what? Let's see. B is a 1. A is changing. C is a 0. So that's my first term. For the wraparound case, I have, let's see, B is a 0, right? And C is a 1. And for the pink group, it is A and B. Could have also been A and C. Let me just write that down. Could also be A and C. That's it. That's the simplest SOP for F complement. Now, if I want to use De Morgan's law, and I would need to use it once I start complementing both sides. Let's try to take a look at what it would translate to. So I have F complement as B and C complement, or B complement and C, or A and B. Now, if I complement both sides, I got a big complement sign over there, but I also get one over here. So I've complemented both sides, shown in red. Double complement cancels out, right? Double negation. I come back to F. And now I can start using De Morgan's law to simplify the right-hand side over here. So what would I get? I would get B and C complement, the whole thing complemented, or becomes AND. This guy complemented, or becomes AND. And then A and B and that. Next, I use De Morgan's law again on each of these three products. So the first one will give me B complement or C ANDed with B or C complement ANDed with A complement or B complement. And that's exactly what you would get if you started combining the zeros in F, right? The zeros in F would exactly be in exactly those positions. And if you started grouping them, you would get exactly that same expression. Well, not unique, because this could also have been A complement or C complement, but you would get the same expression. So a couple of ways to go to the simplest POS. One, group the zeros in F, or start with the simplest SOP for F complement, then apply De Morgan's law. Okay. I will take questions about this example now. Let's also kind of point this out here, that things are not unique. Simplest forms are not unique. Okay, so let's see. I'm going to stop recording here.